Okay, welcome back to Pharmacokinetic Modeling Part B. I think this is where we left off in the first podcast. Again, this shows a one compartment open model with IV administration. You've got one compartment here, that being the blood. You've got intravenous input going into the blood, and then you've got output at some rate, K elimination. And notice, as I said earlier, when the drug is administered IV, in a single rapid injection, the process of absorption is bypassed. Okay. Notice, by the way, there you have V, that's the volume. The D there means distribution, something called volume of distribution that we'll talk about here momentarily. So the one compartment model does not predict actual drug levels in the tissues, but implies that changes in the plasma levels of the drug will result in proportional changes in tissue drug levels, and that's what you'll get to see a little bit with your model that you're going to build for the lab this week. We're going to, again, it's going to be a very simple model, but you should be able to see how the blood levels, how the concentration levels in the blood plasma are changing over time. Okay? Hopefully you've had this in your introductory chemistry course. I'm going to assume that you've had. That may be a dangerous assumption. Again, the word kinetics here means the rate at which some drug changes or some chemical changes over time. And the rate of elimination for most drugs is what's known as a first order process. So you should have seen zero order, first order, second order kinetics in introductory chemistry. And this, again, these values of K are called rate constants, and K elimination is a first order rate constant with a unit of inverse time, such as per hour. So what you should notice on the chart down here are on the left there, I'm just plotting the concentration of drug in terms of milligrams per liter over time. And notice that I have a curve there. So as time decreases, or time increases, I should say, the amount of drug in the concentration of drug in the plasma decreases. On the right is the same data, except now I plotted it on a logarithmic scale. So you see the 1, 10, and 100 there. That's a log scale. And those of you who've studied kinetics know that first order kinetics are logarithms, and you see a straight line there, which tells you that it is indeed first order. So when I plot the logarithm of the concentration over time, and I get a straight line, that tells me I have first order kinetics. Okay. Again, here's the same data. I'm plotting the data, again, concentration, in this case micrograms per milliliter on the y-axis and time in hours on the x-axis. And what you should notice there is something called a half-life, T1 half. That for this particular drug, the half-life is 2 hours. That means in 2 hours time, I have half the amount of drug that I started with. CP0 there, you see there is 100 micrograms per milliliter. So the 0 there says at the beginning of time, when the experiment starts, I have 100 micrograms per milliliter, and again, this is a concentration. Notice micrograms there is a unit of mass, milliliters is a unit of volume. So concentrations are mass or amount divided by volume. Okay, and again, I plot these things on regular graph on the right there. You see basically the same data plotted on just a regular graph on top, and then a logarithmic graph on the bottom. I get a straight line, and that tells me I have first order kinetics because it's a log scale. Okay, this will lose a couple of you probably. Some of you who've taken AP chemistry may have seen this, but the rate of change of drug plasma concentration over time is equal to this differential equation. The D there means delta, or change in. All times you'll see the Greek symbol there, delta. So the change in the concentration in the plasma as time changes is equal to minus the rate constant, K elimination, times the concentration of drug in the plasma. Notice the minus there says that the concentration of drug in the blood is getting smaller. It's never going to get bigger. So if you start with 100 micrograms per milliliter, okay, the concentration can only get smaller unless you inject more drug in. Okay, so this expression shows that the rate of elimination from the body is a first order process, and it depends on the elimination constant K sub EL. And again, those of you who have had a good kinetics background in your introductory chemistry course will recognize this as a first order kinetic relationship. Okay? I might need to help some of you who haven't had kinetics or who don't remember kinetics. That may be something you need to get a little help with this week. Okay? What I do is I integrate, I do some calculus, I integrate dc over dt, I integrate both sides, and what that leads me to are what's called the integrated equations. Again, those of you who have had a good kinetics background in your introductory chemistry course will recognize the second equation there, ln of Cp is equal to ln of Cp at the start minus K elimination times time. Okay, that's the integrated rate law. I know in my chemistry class I required students to be able to write integrated rate laws, and that may be something you have or have not done. Okay. The elimination half-life, as I mentioned earlier, is the time taken for the drug concentration or the amount in the body to fall by 1/2. And the easiest equation there is T1/2 is going to be 0.693 over KEL. The 0.693 there, by the way, is the natural log of 2. So if you get on Mathematica or your handheld calculator and you take the natural log of 2, ln of 2, you will come up with the number 0.693. And you will use that number in your pharmacokinetic model this week. Okay. Estimation of half-life from the graph. If you plot the concentration in terms of some units like milligrams per liter as a natural log or a log plot on the left, and over time you can determine what the half-life is, and there you notice that the half-life here is going to be about 3 hours. Okay, so we can actually estimate that half-life from a graph, and that's the easiest way to do that. Okay. All right, fraction of dose remaining is given by this mathematics there, where E there is an exponential. So I can calculate the amount of drug in the body, and I can calculate how much dose is remaining in the body with time. I can also calculate the fraction of dose lost after a period of time, t, using the 1 minus E equation down the bottom. So lots of things that I can calculate to figure out how much drug is in the body, how much is still there, how much has already been lost, all of that kind of stuff. Okay, volume of distribution, we mentioned that a little bit earlier. That's the volume in which the drug is dissolved in the body. So for example, 1 gram of drug is dissolved in an unknown volume of water. Okay, so the concentration is going to be 1 milligram per milliliter. What's the original volume of the solution? You can do the volume equals amount divided by concentration, 1 over 1. So the volume there is 1 liter. So you can calculate all of these things. If the volume and the concentration are known, then the original amount dissolved can be calculated by the formula there below. What we're going to calculate is you're going to know the amount, you're going to know the volume, and we're going to calculate the concentration. So if you do the algebra there, you should be able to figure out how to do that. Okay, volumes of distributions is called, we're going to use an apparent one because it doesn't really have any physiological meaning. Drugs that are very highly lipid soluble, such as the digoxin, have a very high volume of distribution, 600 liters. Drugs which are lipid insoluble remain in the blood and have a low volume of distribution. Okay. Volumes of distribution are constants. Okay. They are a constant that change for every drug. You look them up in a book of pharmacokinetic parameters. So for the drug that I give you to build your model on, we're actually going to do ibuprofen as our drug. I will give you the volume of distribution, and I'm getting the volume of distribution from a handbook of pharmacokinetic parameters, so we actually look these things up. Okay. If you go on Drug Bank, you should be able to type in ibuprofen, and you should be able to find the volume of distribution for that particular drug. Okay. So volume of distributions are constants for specific drugs. There's some calculations there. Volume distribution is the ratio between the amount of drug and the concentration in the blood or plasma, and we can calculate, if we know volume of distribution, we can calculate, and we know the dosage, we can calculate the concentration, or we can do all those mathematics, okay? And again, there's that mathematics again. So there's some pretty simple calculations we can do here. We can obtain a lot of these values by plotting things on semi-log paper or log paper. Okay? And there's a picture of where I'm plotting things on semi-log paper or log paper. Okay? So we won't ask you to do those. There's something called an area under a curve. We're not going to mess with that here, but we can determine an area under the curve, which is a measure of how well a drug is distributed through the body. We can calculate that using some of these mathematics. Okay. Some of the significance of volume of distribution: drugs can have volume of distributions equal, smaller, or greater than the drug mass. Pardon my phone ringing. Drugs with small volumes of distribution are confined to central compartment or highly bound to plasma proteins. Drugs with large volume of distribution are usually confined in the tissue spaces. We can also calculate these as percentage of body mass, and we can compare these to true anatomic volumes. And as I mentioned earlier, volume of distribution is a constant, but it actually can change a little bit due to the pathological conditions, okay, the disease that the patient has, or it can change with age. So these numbers, volumes of distributions, are typically constants, but they can change based on a disease state or as the patient gets older. And that's something you're going to have to pay attention to depending on the PK model you're using. Okay. Here's a calculation. If I want to calculate the percent of body weight in terms of volume of distribution, I can calculate volume of distribution as a percent body weight. We probably won't ask you to do that. We might ask you to do that in the model and see how that comes out. We'll go from there. Okay. There's something called clearance, which we're not going to spend much time with here this week. There's already enough to do. And that's the volume of blood that is cleared of a drug per unit time. And this is measured in liters per hour. And notice there I can measure the clearance using the formula clearance equals volume of distribution times the elimination rate constant K sub EL. We may throw that into our model just to see what the clearance looks like. But again, that's something we're probably going to not spend a lot of time on this week in the PK model, just because the model is already hard enough as it is. Okay. So here's all these integrated equations, and this would not be a bad picture to print out. I would especially encourage you to look at, say, the integrated rate law there, natural log of the concentration in the plasma equation. I would encourage you to look at the half-life one is one we'll definitely use. You might be aware that there's something called clearance. You might be aware that there's something called an area under curve. All these are important pharmacokinetic values that we need to be able to calculate. And as you move farther up the food chain in medchem, you'll certainly be seeing these on a regular basis. Certainly if you're going to med school, you'll have to be able to calculate all of these very easily. These are equations that most medical students have memorized and use fairly regularly. Okay? And again, we can estimate some of these PK parameters, such as the K elimination, by plotting a lot of this data and going from there, and we may give you an opportunity to do that in a later lab. And I think that's probably, there's K elimination. I think that's probably all for now, and I hope you enjoyed this, and we'll see you online.